Okay, let me turn the TV on. Bless you. Let's try that. There we go. I gotta say, again, I was tickled with how everybody did on the second exam. I thought y'all did great. One thing that I thought was kind of interesting was, so I had given a problem like problem 3 a few years ago, and one of the things I did is I changed up the channel size, and so the intent for the answer was supposed to be this. Was 2 by 4, right? But there were a few of you that here I'll try and do it the same size. There are a few of you that did this. That did 1, 2, 3, 4, 1, 2, 3, 4. That did this. And the thing is, they actually both worked. They both worked from a capacity standpoint and from a spacing standpoint. And so I said, you know what? I'm just going to, if you did that and you did it correctly, I'm just going to give you full credit for it. So I did. Again, I think that you all did very well. I really don't have any like global advice, you know, beyond what I said for the first exam, like for the final, because I think you all did great. So yeah. Sound good? Okay. Welcome back. I hope everybody had a good break. We're going to get right back into it with columns. We have 1 day of columns left, and then we're going to spend the rest of the semester on beams. And then near the end, we take a little bit of a detour for a topic called local buckling, but we'll get to that later. What I want to say is up until now, everything's been graded except for homework 5.3, and then everything else is up to date. So a couple of logistical items before we get to it. So the only thing we have left between now and the end of the semester is just beams and homework assignments to go along with it. And so we are going to have homework, you know, sort of in our regular pattern. There is 1 day that we take a break from the homework assignments. The only thing I'll tell you about the homework from here on out, and I do my best to try and regularize it, but sometimes with this topic in the class it's kind of difficult, and that is that the homework is a little sporadic in terms of its size. Like, for example, homework 6.1 is going to be like the shortest homework we've done all semester. And then there's homework 6.2, which is a good bit longer, okay? And I can't really do anything about that because it's just sort of the nature of the topic. But you'll see what I mean when we dive into this. Okay, so with that, let me stop talking about intro and let's just get right down to it. Let's get into column design. And I'll say I really wanted to sort of finish this before break, but I will say it is kind of nice to sort of revisit it for a day. But also I think this lecture really does put sort of a nice bookend on the topic of columns, because the example that we're about to do is a little bit more involved and it requires a little bit more brain power, which may not be good for the Monday after spring break at 9 a.m., but, you know, is what it is. Okay, all right, so let's get into it. First off, let's make sure that we're all sort of remembering what we're talking about here. So we're talking about columns, and we're talking about sizing columns or selecting columns to support given loads. And so one of the things that involves is the selection of an appropriate K value. The problem that we're going to do today, the K values are all 1, so that part's going to be pretty easy. But know that you can look K up accordingly. Now, if you recall, we have 2 methods for analyzing a column. The first method is to just do the math, and to do the math using section E3. So remember, when we're doing the math directly, we're trying to determine the governing slenderness, not the governing KL, okay? So the governing slenderness, the governing KL over R, is the KL over R that's the longest, so we determine, or the largest. So we determine the largest KL over R, and then using that KL over R, we compute an elastic buckling stress, and then a nominal buckling stress using our column curve equation, and then using that 0.9 times that times AG to get the capacity. I would say that everybody probably agrees that step one is probably the hardest. Like if you can get that, the rest is just sort of plug and chug, okay? Method two is to use our design aid. Now these are analysis methods, right? Now with the design aid, we're not trying to determine the governing slenderness, we're trying to determine the governing KL, okay? And so the way that works is we're basically determining the largest of either KLY or KL effective, okay? Now the way that we do that is we look at KLX and we look at KLY. If KLY is bigger than KLX, there's no need to compute a KL effective. You know that the weak axis is going to govern. Just look up a section and or look up the capacity, and there you go. But if KLX is bigger, you can't compare KLX and KLY. It's comparing apples and oranges. To compare apples to apples, we need to adjust this KLX into an effective KL, okay? And the way that we do that is we take KLX and we divide it by that RX over RY ratio. So we have a KLY and a KL effective, and we take the largest of those, okay? Now, when you look things up in table 4.1, chances are you're not going to be looking up pretty values like a KL of 14 feet. You're going to be looking up a KL of 14.623 feet, and so you have to interpolate, okay? So more often than not, you have to do that. Now this is great for analysis, but for design, which is ultimately I think what we're really after near the end of this topic is, well, let's go through that, okay? So to design a column, we determine our factored load, we determine the largest KLX and the KLY for the column, but we look up trial sections based off KLY, okay? Now remember, for trial sections, what we're doing is we're trying to find at least one W14, one W12, one W10, one W8. Some of those, it may not be possible to find one, and I think our example today, that is in fact the case. But basically all that means is that sometimes you got some really big loads and maybe a W8 just doesn't work, okay? And you'll see what I mean, I think, today. Now I say that these are trial sections, especially if you have a situation where the strong axis governs, because you need to validate each one of those sections. Now if KLY is bigger than KLX, that there's no need to sort of validate it because you know that the weak axis governs. You looked the section up based on the weak axis, so you know they work, so just pick the lightest one. But if KLX is bigger, you got a little bit more work to do. And what I'll say is that if this step here was a little confusing, maybe today it won't be, okay? So I think this is the day that really sort of ties everything together. And I'll also say that this is the day where you really need to put your thinking cap on in terms of understanding how columns behave. We're going to be able to make a lot of inferences and use a lot of critical thinking in our design process. And so to explain that, let's just go through a problem, okay? So let me pull this up on the notebook. There's my sound effects again. Okay, so this is going to be our problem for the day. So we're going to be looking at a column here that's 32 feet long. Now it's 32 feet long, but along the weak direction, or the weak axis, it is braced, okay? There is a brace in the middle, okay? Now I know that everybody brought their AISC 16th edition steel construction manual, right? Everybody brought it? Because everybody brought it? You're going to need it today. That's not the 16th edition. There's the 16th edition. Okay, you are going to need it today. Okay? Now, as I said, K is 1.0 for all these segments. If you look, every segment here is pinned in either direction, okay? So K is 1 for every segment. That part's going to be easy, okay? Now, what we're going to do is we're going to select the lightest W shape possible to resist a factored load of 650 kips. So I kind of wanted to get to the meat of this example. We're not even going to have to worry about factoring the load. I mean, step one is to determine the factored load, but we know that PU is 650 kips from the problem statement. So we can sort of like move past that, Okay, so what I want to do is I want to determine the appropriate column to resist these loads. Okay, now let's just follow our process sort of verbatim for now, and let's see if we can discern how we need to go about this. Okay, so in order to design a column, we need its load, but we also need the KL values. Okay, so let's determine the largest KLX and the largest KLY. Okay, now for this column, I think it's pretty easy. KLX is going to be what? Make sure everybody's awake this morning. $32 feet. And KLY is going to be, there we go, 16. Now to be clear, I mean, this is a really realistic bracing scenario. This is what you would do in the real world. I mean, if I have a 32-foot column and I want to make that column stronger, I need to brace it. But if I'm going to brace it, which direction am I going to brace it? I'm going to brace it about the weak axis, not the strong axis, right? If I press that column and it's going to buckle about the weak axis. So placing a brace right here in the middle along the weak axis is what you would do. Like that if you're going to make the column stronger, that's what you would do. You would brace it about the weak axis. Okay? So again, I didn't want this part to be complicated with this example. I want to get to the actual process of design. Okay? So let's get into this. Okay? So the first thing we need to do from a design standpoint is we need to select some trial shapes. Okay. Now, remember, so we're using table 4.1 to select trial shapes. Now, table 4.1 is written based off of the y-axis, okay? So we're going to be selecting trial shapes based off a load of 650 kips and off of a length of 16 feet, because that is the length along the weak axis, right? I mean, table 4.1 lists the capacity with respect to buckling about the weak axis. This is how long the column's effective length is in the weak axis. So this is what matters in terms of selecting a column, okay? Now, so we need to select trial shapes. So I'm actually going to number these. Let's number these. We'll letter them. How about that? So we need to select the W14. Okay? Remember how we do this? We select a W14, a W12, a W10, a W8. So everybody's got their AISC 16th edition steel construction manual, right? So help me out. Okay, so we're going to go to table 4.1a. And we're going to find the lightest W14 that we can. The lightest W14 we can that at a length of 16 feet, at an effective length of 16 feet, I should say, can resist 650 kips. What's the lightest W14 shape that you can find? 82. Okay. Is anybody else seeing that? Okay. I'm seeing a few people say that. Okay, so a W14 by 82. Okay, now you selected that because it has a capacity of what? Let's go ahead and write that down.
697.
697. All right, because if you go to the next lightest shape, it's too low, right? Now, before we move away from the W14, I want to also record the RXRY ratio. Let's go ahead and write that down. We're going to need it here in a second. Well, we might need it. We'll see. What is the RX over RY ratio for this one? 2.44. Now, before we move on, is everybody able to see these two values? And if you are not, tell me that this is important. Okay? The Rx over Ry ratio is at the bottom. And then again, we're just going to 14 feet and finding a W14 by 82. Okay? Everybody good with that? Now this is a trial shape. Okay? I say trial shape. I don't know whether or not it works because I need to check the strong axis. Okay? But we'll get to that. Okay? All right, how about a W12? And somebody else answer this. Somebody maybe in the back. Find me the lightest W12 that works. Say it again? 72. Okay. Is everybody else seeing that? Everybody else seeing that? Now, why did you pick that? What was its capacity?
709.
And while we're at it, what is its Rx over Ry ratio?
1.75.
Okay. Is everybody else seeing that? Everybody able to find that? Then we're just going through the W12s, finding the lightest W12 that works. Okay? How about the W10s?
77.
Okay. Now, why'd you pick that? 686. And what about its Rx over Ry ratio? I'm going to scroll up a little bit.
1.73.
Okay. So far, so good? Okay, now how about a W8? Say it again?
There isn't one.
There isn't one, right? What's the heaviest W8 available?
487 or 67.
W8 by 67?
Yeah.
And at 16 feet, what is its capacity?
487.
487, right? So the heaviest W8 available just isn't enough, right? So we'll say no W8s available, okay? And let's just like put some context here. Remind me, if I have a W10 by 77, what does the 10 mean? What is the 10? The depth, right? Okay? A W8 is about that deep, and it's supposed to hold up 650,000 pounds, and it's 16 feet long. Like, you see what I mean? Like, just think about it. Like, it's not unreasonable that a W8 isn't going to work, okay? That's a lot of load for a steel column about that deep. You know, that's really tiny. So don't think that's a problem if you can't find one. Just, you know, keep the context alive. Okay. All right. Is everybody with me so far? Now, we did a problem like this before break. And the issue was the problem that we did before break, we had this situation. We had that KLY, so the problem we did before break, I think it was KLY was something like 14 feet and KLX was something like this. I think that feels right to me. Okay? And the problem we did before break, if these were our governing values, I know that this governs. Okay? And if I know that the weak axis governs, what that means is I know that all these shapes work. So I'll just pick the lightest one, and of these, the 12 by 72 is the lightest. I'm done, right? That's not the case with this problem, okay? With this problem, I've got that. So the question is, does the strong axis govern or does the weak axis govern? I don't know. In fact, it's possible that maybe for this one, the weak axis governs, and for this one, the strong axis governs, or vice versa, okay? Whenever KLX is bigger, what that means is that we have to investigate the capacity of each of these trial sections, and that's what we're going to do, Okay? Now, just so everybody's clear before we go into this problem, I am going to do this in order. Okay? I'm going to do section A, then I'm going to do section B, then I'm going to do section C. Okay? Then what we're going to do is we're going to go back and go, was doing it in order the right way? Did that make sense? And maybe it doesn't. Okay? But I'm doing it in order because each of these are going to give us a unique viewpoint as to what can happen. So I'm just doing it in order for the sake of doing it in order. So let's just do each of these in order. Let's start off with the W14 by 82. So while we're doing this, turn to the W14 by 82 because we're going to need to go back to that table. We're going to need some stuff. Okay? All right. So for the W14 by 82, the KLY is 16 feet. What is KL effective? It's KLX over RX over RY. Okay? And what is that? 32 feet divided by what? 2.44? So, what is that? 13.11. So, for this column, which axis governs? The weak axis or the strong axis? Remember, when I say govern, what do I mean by that? I mean that if I have this column, right? So what governs its capacity? Remember, a column is governed by its slenderness, right? The bigger the slenderness, the larger the slenderness value, the weaker the column, right? And so these are just normalized expressions of slenderness. So the longer these dimensions are, the weaker the column, right? So what governs its capacity? Its weak axis or its strong axis? It's weak axis, right? Because it's longer in this direction than it is in this direction. So it's going to buckle this way first, right? That's what we mean when we say govern, right? So KLY is greater than KL effective weak axis governs. And what I mean by that is if the weak axis governs, then what we looked up truly is the capacity. This table is written assuming that the weak axis governs. So I propose that the capacity of this column is in fact 697 kips. So let's just ask a blunt, straight, basic question. If I were to use a W14 by 82 for this column, would it work? Yes. Yes, it would. Okay? So I'm going to say that trial section A is adequate. That is an option. Okay? That's an option. And so we could stop the problem right now. We could just stop and just use the W14 by 82 and go home. Okay? So I guess a question for the class is, what benefit would there be in checking the W12 by 72? Why even bother?
Because it's lighter.
Because it's lighter. That's exactly right. I might be able to get a lighter section, right? With me so far? So let's check the W12 by 72. Let's see what happens. Okay. Let's see what happens. So again, for the W12 by 72, again, we still have the KLY of 16 feet, but what about the KL effective? Bless you. What was the RX over RY for this? Say it again, 1.75? Okay. So what do we got here? 18.29. Okay. So tell me what's going on with this column. The strong axis governs. Okay, so what does that mean? Okay, so first off, okay, let's just write that down. What does that mean? Well, what did it mean up here? What did it mean for section A? Section A, the weak axis governed. Okay, so what did I say after the weak axis governed? The weak axis governed, therefore the capacity is 697. So I just said that's the capacity. Why did I do that? Well, these trial sections were looked up based on the weak axis. So because for the W14 by 82, we found the weak axis governed, that is the capacity. So I guess my question for the class, is this the capacity for the W12 by 72? No, it's not. That's wrong. That's what we mean when we say verify the trial sections. This is not the capacity of the 12 by 72. So what is the capacity of the W12 by 72? Well, the capacity is based on this. So we need to look up the capacity based on 18.29 feet. Can we look up the capacity based on 18.29 feet? No. But we can look up 18 feet and 19 feet and interpolate. So let's do that. Okay? So what we're going to have is an 18-foot value, an 1829 value, and a 19 value. So somebody help me out. What is the capacity for a KL of 18 feet? $656. Everybody else see that? What about 19 feet? $629. So it needs to be somewhere in between there, right? And remind me, what was the load on this column? Like, what are we designing it for? So it needs to be somewhere in between. Seems like it's worthwhile to interpolate, doesn't it? Let's see what happens. So what do we got? We got I think that's about right. What do we get when we interpolate there? Did I do that part too fast? I mean, that's just linear interpolation. 648, we'll say 648.2. Do I have a second? So 648.2. First off, I mean, does that sort of pass the smell test for linear interpolation? I mean, it's got to be in between these two, right? You know? So what does that mean? Does the 12 by 72 work? No, it doesn't, right? So here, I'll box this so it's sort of by itself. All right, so we'll say that trial section B is inadequate. That one's not going to work. So, could we stop right now? Well, you're saying no, why?
W10 be lighter.
Exactly, right? So, exactly what I was going to say. So, I mean, we have a section that works. We have the W12 by, or 14 by 82. But it's still worth it to check this next section because it's lighter, right? Okay. And remember, you always do want to kind of keep your eye on the prize. The eye on the prize for this problem, or the prize for this problem, is this number right here. If we can get a capacity that's greater than or equal to that number, then we know the column works. Okay? So let's see this W12 by 77. Let's see what happens. Okay. So we do our KLY, we do our KL effective. I'm sorry, what was RX over RY for this? 1.73. Which is what? 18.50. Second? All right, so observation, which axis governs? There we go. So, whenever we say the strong axis governs, what we mean is that capacity that we looked up, add that in the capacity, okay? We have to verify that capacity, and this is saying that capacity is not right, okay? Now, can we look up 18.5? No, but we can look up 18 and 19, right? So, let's do that right here. Now, first off, if we do the linear interpolation, it's going to be pretty easy. You just average it, right? Okay, so what do we get for 18 feet? 617. Okay, and what about for 19 feet? Okay, and so we want to find the capacity in between, but anybody make an observation about what we got going on right here? It's not going to work, is it?
It's already lower than 650.
It doesn't matter. Exactly right. It doesn't matter, right? So, is there any point in doing the interpolation? No. Is this column going to work? No, it's not going to work because it doesn't matter what this value is. It's less than this. So I guess my question is, now do we have our answer? Yeah, we have our answer. The first section, the W14 by 82. And so, what is the answer, by the way? What's the answer?
Cross section A.
And what is that? That's our answer. Now, personally, I don't believe that the problem is done, okay? Because I think after all this hullabaloo, it's worth it to just analyze the W14 by 82 and make sure that it works, okay? Especially with problems where you ended up selecting a section based off interpolation, where you've got multiple different iterations and trial shapes. Just analyze it and make sure that it works, okay? So we are going to analyze it, but before we do, here, I'll just set a trial section. We'll just say analyze W14 by 82. I mean, if you ask me, a column that's going to hold up 650,000 pounds is worth 3 minutes of calcs. I'm sorry, I think it is. Okay, so we're going to analyze it just to verify. But I do want to go back to some of our process here because, first off, I want to make sure that the process made sense. I want to make sure that you all have an understanding for when interpolation is a good idea versus here when interpolation really didn't make any sense, okay? And to be clear, I have no problem if you get to a point where, okay, for example, we had this. So we had what, 617 and 582, and we'd said that the section does not work, right? But let me ask you a question. What if we had gotten this? What if that's what we had gotten? What could we say there? We could say that the interpolation is not necessary because the section does work, right? Because no matter what, it's going to be bigger than this, and this is bigger than that, right? So that's fine too, okay? Make sense? Now, here's another question. Without going through all this math, what do you think might be the easiest way of doing these? What order? Do the lightest one first. So whenever you find one that works, stop. You see what I mean? We didn't do that for this problem because I kind of wanted you to see all three different iterations. Although we could have done it in order, we would have seen all three. But what I'm saying is I have no problem if on an exam or on a homework assignment, you do it in order, and if the first one works, you just stop. That's fine too. You don't have to do them all, right? The whole point is to select the lightest shade, okay? Now for this one, it happened to be the first one, You don't really know that going into it, right? There's too much going on. That's why we have table 4.1, okay? Does that make sense? Now again, I think that this is worth 3 more minutes of our time or 5 more minutes of our time if it's going to hold up 650,000 pounds. So let's analyze the W14 by 82. Now I'm going to help you out a little bit. Here's AG, RX, and RY for the W14 by 82. And I'll just get these right from the very beginning of the manual, table 1-1. Now some of them are at the bottom, but not all of them. So I get into a habit of just looking them up directly from table 1-1. Now remember, we do still have these. And I want to be clear, we're using KLX and KLY. We're not using KL effective here. Okay? KL effective is just a tool for using table 4.1. We're not using table 4.1. We're using the spec directly. So we can ignore all that KL effective junk. Okay? So how are we going to handle this? The first thing we're going to do is compute a KL over R for each direction, right? So that's going to be 32 feet over 6.05 inches. Am I missing something? What am I missing? There you go. You got to convert this to inches so that it's inches over inches. Remember, slenderness is dimensionless. It has no dimensions. Okay? So we'll do the same thing here. So somebody give me a KL over R for the X and KL over R for the Y. What's KL over R for the X-axis?
63.47.
What about Y? 77.42. Make these sevens a little clearer. So which axis governs? Weak or strong? What was that? No. These are slenderness quantities, right? Bigger the slenderness, the weaker the column, right? So we're trying to figure out worst case scenarios here. Now, does that gel with what we did before, right? When we analyzed the 14 by 82 up here, what did we find? Here's the W14 by 82, and we found that the weak axis governs. Down here, this is the weak axis. Right? So now what do? I've got the governing KL over R. What do I do with it? What's the next thing that I compute? What's a Fn? But in order to get Fn, I'm missing a parameter. Fe. What's E? There we go. It's like 62.4 pounds per cubic foot. I want that number just burned into the back of your head, you know? What do we get for this? Remember, don't forget to square that at the bottom. Do I have a 7 or a second on that?
Yep.
I know I have a 7. I have 2 of them. All right. Okay. Now we've got to compute Fn. But we can't compute Fn without figuring out which expression to use for Fn, right? Because remember, we have an inelastic buckling expression and we have an elastic buckling expression, right? So the way that we figure that out is we say KL over R is 77.42. And we compare that against what?
4.71.
There we go.
Multiplied by the square root of the E over F.
All right. And that one I'll give you. That comes out to be about 113. So, therefore, we calculate our nominal buckling stress as we use the exponential term, which, by the way, during design, if this isn't happening, you're probably doing something wrong, okay? Just about every column that we design should be using this expression, okay? I'm just throwing that out there. If you're not using it, chances are you're doing something wrong. Because inelastic buckling allows the column to reach higher stresses, which is kind of what we want in design. We want to be able to use as little steel as possible. So if we're using as little steel as possible, the steel that we do use is probably going to see some pretty high stresses. So that's kind of why. Remember, that's an exponent. So what do we get for that? Remember that fraction, it's an exponent. You're not multiplying by it. 93.75? Yeah, I'd check that. That seems high. Like 32.26? Yeah. I was going to say, that seems high. It can't be higher than 50. Okay, and then AG was 24. Woo. Okay, hold on, I can do better than that. Okay, and so what do we get for VPN? So what does that mean? Is that good? That's good, right? And by the way, what did we get for VPN from step 4? 697. And we just calculated 696.8. Just saying, So I'll just call it, capacity verified. And again, for a column that's holding up 650,000 pounds, I think it's worth 5 minutes. Make sense? All right, any questions on this? All right. So, as I'm sure you can expect, I got a problem like it. So here's the problem. And again, this is that this boundary condition right here is the one that translates but doesn't rotate. So I think this K value, or I even gave you the K value. I made it easier even there. So I've got a K value here, K value here, K value here. Same sort of idea, okay? We're gonna design this for a load of 725. I want to see what you do with it. Sound good? All right, I'm gonna pull up the code one more time, and I will see you all on Wednesday.